All right, so this section is going to be about network security infrastructure. The main things out of this section, there's no labs like we talked about earlier. However, there are some packet tracer activities. And so if you guys get a chance, you certainly have the time and opportunity to go do those packet tracer activities to help reemphasize what's going on in the class. They're heavily recommended by Cisco to help reinforce those concepts. All right, so most of what the network security infrastructure module is going to talk about is dealing with network topologies and how they're designed to influence the flow of traffic through a network, different security devices such as specialized hardware that will help enhance network security, and then network security services, which are going to enhance the level of security within the network. So different topologies, there's different network representations you'll typically see even with Cisco, but these network diagrams are often called topologies, and they use different symbols to represent different devices and connections throughout the network. In particular, terminologies that are known as things like network interface card or a NIC, a physical port, or an interface. These icons that you see on the right-hand side, it's always best to draw up your topology no matter how small your network is, just to give you a quick visual of what's going on. So end devices up at the top, you can see the list of those there. Your intermediary devices, these are going to be your switches or your routers or firewalls. And then the type of lines that you use for connectivity, typically a dark black line is going to be your LAN media, the squiggly being your wireless, and then the one with a, the red one there represents a WAN connection. However, that WAN typically, you know, it used to mean serial, but these days there isn't much for serial interfaces. So different topology diagrams, you'll see both physical topologies where you're talking about the actual devices over here and where they're physically located, etc. For example, rack 1, shelf 2, etc. And then you'll also see ones that are logical, that are simply just illustrating where the device is and the IP address schemes, etc., with the interfaces that they're connected to. Obviously, there's networks of many sizes. You have the small home or the Soho office. You also have the medium and large, and then, of course, the World Wide Web that's on top of that, connecting millions of computers together. So on LANs and WANs, the network infrastructures vary greatly, the size of the area that's covered, the number of users, area of responsibility, etc. Typically, you're going to have a LAN, which is usually shaded different than your WAN connection that goes on the inside. So this is going to be your cloud or your ISP provider, and then everything inside of that router going in is going to be considered your LAN or a local area network. You may have multiple networks inside of there, but that's all going to be referred to as the LAN side of things. Between the LAN and the WAN, a LAN is going to be a small geographical area where a WAN is going to span a wide geographical area. Even if you have different branches, so say you have different buildings, the connectivity between those two different buildings is going to be considered your WAN connection, whereas the LAN is everything inside the building itself. Even with VPNs, those are still considered to have a WAN connection to the home, and then it puts you on the LAN, which is just logically going to transfer that traffic as if you were on the LAN. In the 3-layer network design, you're going to see this here. So you always start with the access layer. This is where almost all of your switches are typically going to be, or wireless access points. From there, you're also going to have the endpoints here where your phones and such are, but that's even further down. Typically, that access layer is dealing with these switches here. Then you have a distribution layer. These are usually in the larger networks, and what that's going to do is combine or aggregate access within the access layer. So this may be routed, as you see here, they're referring to it as layer 3 distributed switches. But you could also have your core layer, which is going to be the core connections up above. And so if you were running a data center, like this core layer would be something like the old Cisco 6500s, big, bulky switches, weigh hundreds of pounds, with lots of connections and points on top of that. And then you get out to a distribution layer, which is going to be more of a switch that's going to have interconnectivity to up above, along with some redundancy, but you're really going out to all the in-layer switches that may be in all the buildings, etc. So say this was on like a school campus. Your access layer is going to be the closet that's going to be out there right next to the PCs and the computers and the printers, etc., that are on the network. Your distribution layer is going to be like per building. So per building, you have one distribution switch. This access layer is going to be the various switches in the closets for the different departments. And then if you're at the core layer, this is going to be back in the data center where all these distribution switches are coming back to. So although there's 3 layers, there's some smaller networks where it just has a collapsed core. And this would be most businesses, et cetera, where you're going to have either a routed or a switch layer here that then goes up and brings that in there. So you typically don't have that core / distribution layer. You just don't have the design or the need for it if you don't have that big a space. So some common security architectures that you're going to see, you typically deal with what's called a public network, is often referred to as the untrusted area. And then you have a private network, which is your trusted zone. This is typically referring to zones as familiar within firewalls. So again, your private or trusted zone is your devices, things that you trust on your network. However, we don't trust anything out there on the internet. You could have all sorts of things. So we typically would start with basic layers that they're going to go into here, where we allow traffic outbound, but we do not allow traffic inbound that wasn't originated from the inside. And that's called stateful firewalls, which we'll talk about. So here you see a firewall / router where you're taking traffic in. It's going to have the rules that allow it to be outbound to the internet. We also have what are referred to as a DMZ or a demilitarized zone. This is typically where you have your servers running. Usually there's connectivity directly to the public so that the interfaces or the traffic would seem like it's going directly to the public. And this is going to be like your web servers, etc. You don't want that inside your private network where your PCs are. You want to have it off on its own zone. And that way you can limit those with different rules and monitor the type of traffic that goes through there. So now you have traffic outbound to the internet, but doesn't have an inbound unless it's permitted here. You see you have selectively permitted traffic going directly from the internet to the DMZ. And then from the private inside, even going to access your own web servers, etc. You have, inspected permitted traffic over here with no traffic being able to come directly from the DMZ back unless initiated. And that gets into zones. And so that allows us to have zone-based policy firewalls or ZPFS. Typically, this concept is just to provide flexibilities. You want as many zones, which is basically a group of one or more interfaces that have similar functions. And they'll help, like here they say that they'll help specify a Cisco iOS firewall rule, but that works for any zone-based firewalls. It's the same way. So down below here, you can see that this group was probably, something that's like the HR department. And then this group over here, maybe accounting. They need to talk to one another, but we split them into zones so that if we need to provide rules between them, we can do that. And the more zones you have, the more rules that you have to create, but it also gives you the flexibility of locking down more traffic. So you have the public one over here as well as the DMZ over here. So there's some packet tracer activities, again, that you can go through and do this. You're welcome to do that. They're not going to be required, but it may help that understanding that's going on. With different security devices, the ones that we're going to deal with are going to be firewalls. And a firewall is basically a system or a group of systems that enforce an access control policy between networks. So they're resistant to network attacks as it typically denies all traffic unless it's permitted, only transition point between the internal corporate network as well as the external network. So for example, here in this animation that you'll see within the class, they'll only allow certain types of traffic. And so you have to have all these policies in place to allow certain traffic through, the rest it all rejects and denies. So benefits of that, it's going to prevent exposure to sensitive hosts, resources, and your applications from untrusted users, aka the internet. You're going to be able to sanitize some protocol flows, which prevents the exploitation of certain protocol flaws. For example, that whole SYN ACK that we talked about on a TCP side, if we're noticing a bunch of SYNs come in that shouldn't be there, we're going to block that type of traffic over time. Any type of malicious data from servers and clients, it's going to block that, as well as reduce security management complexities. So the only negatives to this particular type of configuration, as a misconfigured firewall can have severe consequences for the network, being a single point of failure. So you definitely need to have some redundancy on your firewalls if you're going to have a larger network. The data itself for many applications can't be passed over the firewall securely, which means you're going to have a higher end firewall in order to accomplish that. The more secure traffic that flows through a firewall, the faster the interfaces have to be, because you're inspecting every packet that comes through. So you may have heard of DPI, or deep packet inspection. The firewall, depending on how good it is, has the ability to drill clear down to layer 7 and find out exactly what application you're using there, so that we can identify it and either allow it or not allow it. Typically, most generic firewalls are just going to do this based on port. So you could be looking at port 22, or you could be looking at port 23. But the higher end firewalls, they're actually going to look at the application itself, look in the packet header, and analyze the data on the fly. Obviously, that takes some pretty good processing power, and so it can't do raw packet forwarding at line speed. So if you have a gigabit port on a firewall, you may not necessarily be able to put gigabit traffic through that. Typically, it's a slightly lower amount. If you start throwing secure traffic on there and not just doing NAT style traffic, then it's going to be significantly lower yet, as it's going to have to do SSL encryption in order to get that traffic across there. Unauthorized traffic can also be tunneled or hidden as a legitimate traffic through the firewall. So if your firewall is opening port 80, but you're doing nefarious things through a connection of port 80, the firewall doesn't know that, right? And that comes back to whether it's doing deep packet inspection or not. So you can have packet filtering, which is just going to be a stateless style firewall. What this is going to do is be a part of the router itself. It just permits or denies traffic based on layer 3. So whether an IP address is permitted or a destination IP address is allowed, that's what's going to do that. It's typically known as a stateless firewall. It's just a simple policy lookup is all it is. The more popular ones and more expensive ones are going to be your stateful firewalls. And these are more versatile. As most common firewall technologies that are here, you can see anywhere from layer 3 all the way up to layer 5, and they provide stateful packets. So we can make sure that that session is there. We can make sure the type of traffic there. And even some firewalls will go clear up to layer 7, where they're doing deep packet inspection to figure out what that application is. So that's what you see here is an application gateway firewall or a proxy firewall. What that's going to do is filter information based on 3, 4, 5, and then also up here at the 7 layer. A lot of what we see are these next generation firewalls, and so they go beyond that network or that stateful understanding. They have integrated intrusion detection. You used to have separate devices that would be monitoring and looking for intrusion detection. They also have application awareness, so you can block risky apps for your users. There's different upgrade paths to include future information needs and techniques to address evolving security threats. So there's a lot of next generation style firewalls out here. Obviously, being a Cisco class, they're going to talk about their ASAs, but there's lots of other vendors out there that have next generation firewalls. For example, for you students that are in the cybersecurity realm, you should be going through the Palo Alto program, and the Palo Alto program will take you through their next generation firewall that can do all of that deep packet inspection I was talking about. With this host and server based firewall, this is just going to be a PC or a firewall software running on it. For example, Windows Defenders, which you're going to see on a PC, or Windows Firewall. You can have a transparent firewall that's just simply filtering IP traffic from a pair of bridged interfaces. This can also be a PC. We can run a Linux-based firewall, and you'll see that here. And then you have a hybrid, which is just a combination of these running in between. So what are intrusion prevention and detection devices, typically known as your IDS for intrusion detection and IPS for your intrusion prevention? What these are doing is constantly monitoring traffic and looking for fast moving attacks. So if, for example, we start seeing traffic come over here, comes in from the outside, goes through our router, hits this IPS sensor here, it's going to just send it straight to the bid bucket. The first packet it's going to allow through, but then once it identifies it as bad traffic, it starts sending it over to an empty black hole. IDSs have no impact on the network, no latency or jitter. There's a little sensor failure, doesn't change anything. It just stops being able to prevent the attack or detect anyway. And then your response is it can't stop triggered packets. So what's going to mean there is that it takes some fine tuning in order to get IDSs to work correctly. And that way it's not detecting legitimate traffic and sending it off to the bit bucket. They're a little more vulnerable to network security evasion type techniques. However, an IPS is going to stop trigger packets that are going to be coming through. So in other words, this is like the full-on prevention, right? So this is just going to detect after the traffic is already there. This is going to try to, in real time, prevent that packet from ever coming in. And so it can use these stream normalization techniques in order to do that. The problem with that is because it's doing that, the sensor can overload and impact the network performance, adding latency and jitter and things like that. You can also have some sensor issues that are going to affect network traffic. So they typically complement one another. For example, this is, again, prevention. This one's going to detect something that got through the IPS and now can also send that traffic away. They work in harmony. So deciding which implementation to use based on security goals of the organization stated in whatever network security policy is written. So there's a couple different types of IPSs. You have host-based IPS as well as network-based IPS. On a host base, this is going to be referred to as a HIPS. And this is software that's installed to host and monitor everything in there. So some of you may have used some of these in the past, whether it was Norton or maybe McAfee or there's a ton of different firewall programs, Sophos out there now. Those are all going to be host-based IPSs and firewalls. They may also do the role of antivirus and things like that prevention. The problem is with these style is they got to be installed on all the hosts. So if you just do it on one or two, it's only going to protect that particular host, but you have to end up installing it on all your hosts in order to be secure. With a network IPS, then we're going to be implemented with dedicated hardware. So as you see here, we're going to have untrusted come into our firewall. We have a sensor before we hit over here and do our web servers and DNS servers. And then we have a sensor going back to our corporate network where we have a management server that then hits the route, another sensor to make sure that we don't have traffic going between PCs and going through there. So it's far more robust than just a simple on the host and catching it on this area here. You can actually have integration with both the hosts that would integrate with these network sensors, and then it provides even more robust security. So a Sophos appliance is a great example of that type of scenario. So Cisco has a few software appliances that are available. For example, they have their advanced malware protection. That's going to be doing malware analysis and comprehensive malware protection for the entire organization, all before, during, and after an attack. So it's got combinations of IDS and IPS. You also have the Cisco Web Security Appliance. This is going to be particularly on the web gateways that are leading protections and growing challenges for security and controlling web traffic. It does protect automatically blocking risky websites based on what a administrator sets up. And it follows a bunch of blacklists and things that you can subscribe to. You also have the Cisco Email Security Appliance. This is just going to help mitigate email-based threats. So it's monitoring, looking for phishing emails, spam blocking, other malware attached to emails, things like that. Outside of the hardware equipment, we also have security services. Services is going to be, initially, you can do some basic traffic control with just simple ACLs. So what are ACLs? ACLs are access control lists. There are a series of commands that control whether a device will forward a packet or drop the packet. And these all work in order. So the order of your ACL is highly important. It's going to determine which rule is hit first. And so you want your most precise rules to start at the top and then work their way down to the bottom. With your ACLs, it's going to limit just pure network traffic, typically incoming IP address, that kind of thing. You can also block a little bit of your ports if you wanted to. And deny things like FTP or web access, etc. And you can screen or permit deny host services there as well. Some important features of ACLs: you have the standard ACLs, which is just going to either permit or deny traffic from a particular IPv4 address. Then you can get into an extended ACL, which is going to allow you to determine the protocols that are running over that IP address. What are the source IPs, destination IPs, being able to do source TCP and UDP ports as well as destination, and then optional protocol type information for even finer control. So you can do a combination of standard and extended ACLs to create either a number or a name to identify the ACL itself and the list of statements. And this is typically referring to an ACL, like here they're doing it in Packet Tracer because this is common among your Cisco routers and switches. SNMP, you definitely want to be familiar with the concept of SNMP, which is the Simple Network Management Protocol. This is just an application layer protocol that provides a message format for communication between managers and agents. So as you have more and more network devices out there on your system, you typically need some kind of monitoring, and that is where SNMP comes into play. So SNMP is going to alert what's going on that current router, or switch or firewall device, and you're going to get what are called traps. And traps are going to be just snippets of information from these different devices, which are running an SNMP agent on them, and it's going to send those traps back to a collector. Or the collector can individually go get information with her through SNMP gets. You can also set devices through SNMP set. So that means that I can configure routers and switches without having to go to the console. I can use SNMP to send specific commands. This is great for management of the network in order to configure all the devices at once. I can use a series of SNMP sets in order to get that objective done. If I want to pull back information from a particular device that isn't coming in a trap, then I can use SNMP gets. You can also use what's called Netflow from Cisco. If you're using open source standards, you'll have things like SFlow for switches, or JFlow is particular for Juniper devices. They're all similar in what they do. The idea is that it's going to provide statistics on packets that are flowing through the router or the multi-layer switch. So what this is going to do is give you some security and things that are going in there. But the idea is that I can get an idea of the type of traffic that's going through my network. And this all basically puts a sampler out on a switch, which is mirroring traffic out. The collector is going to take a given sample of data. So it maybe takes every 100 packets or every 1,000 packets. It's going to take a sample. Depends on how powerful your Netflow collector is. And what that's going to do is send that type of traffic over to this. So I can get an idea of, this is the amount of Steam traffic that's going over my network right now, or this is the amount of people browsing the web, or this is the amount of FTP traffic going on my network. It gives you great statistics and graphing so that you can have an idea of what's going on the network in real time. To accomplish that, you have to use some features called port mirroring, which is handy. What that does is if you have a switch up here and you have it connected to a PC, right? You can actually send a copy of whatever's going across that port out of another port, and you can have a packet analyzer over here. For example, Wireshark going on. So I can put a Wireshark on a switch on a corporate network, and you'll notice that I don't see much. I'm only going to see what's getting broadcasted, right? And that's because a switch, if you remember, helps break up the broadcast domains. So if I want to sniff a particular user's traffic, I need to mirror the port on their switch to send it over to me so that I can analyze that in between. You could also monitor the traffic, as it says down below there, with another switch, so you can mirror that traffic going down. You can also have Syslog servers. So just like Netflow, where it's sending information back to a user, or SNMP that's using traps, we may use Syslog servers. So we all know about logs and different things that are going on all these different devices. Instead of having to log into every single one of these devices to check the logs when something goes wrong, we have them all sent and forwarded to what's called a Syslog server. And so a Syslog server will take all sorts of messages. It could be just errors. It could be warnings. There's different levels that you could have for logging. And it's going to send it all to one location. And the benefit is I can then do searches for a particular traffic going on my Syslog server, and I can read through all the logs and comb and interlace all the different logs from different routers and switches, firewalls, etc. Extremely beneficial when trying to troubleshoot what's going on. It also makes sure that you're running things like NTP, or your network time protocol, to make sure that all these logs are in sync. If you've got different times on different devices everywhere, then the log information is almost worthless because you don't know what time is true time going on. So you want to make sure that you definitely have all your time set correctly on all your devices, that they're using a NTP server, which is commonly associated with your Syslog server, so that everybody's running on the same time and time zone, etc. Which falls in NTP, which is what we were just talking about. So this is going to be a manual configuration, and using this on all your different systems. The NTP system itself is just a hierarchical system. So you have these Stratum servers that are running out there on the internet. Stratum 0 gets its time straight from authoritative time sources, and then it's going to go directly connected down to Stratum 0 and Stratum 1. Stratum 2 is going to go through NTP clients that are going to synchronize their time and move up. Stratum 3, you can see here, has multiple connections, and then they transfer that time down. So typically, you're going to use different servers that are out there and available for NTP. You could also run one local if you want to run those services local, if you can give a specific time within your network. AAA servers, these are typically referred to as authentication, authorization, and accounting. These are going to be similar to what you can use for user administration, for both logging in, allowing access, SSH access, etc., that kind of thing. You typically want to have this on all your devices so that you can have one database of users and administrators, so that you don't have to have multiple users and administrators on every single device that's out there. So if you're familiar with concepts of LDAP, or lightweight device access protocol, you can also have things that are directory, or you could have, like in a Microsoft realm, you're going to have things like Active Directory. Same concept, only it's for network devices. The idea is that it's going to set up different architectures, and then you could have transport going through there. Cisco has two different ones that they typically use. They have what's called a TACAC server, as you can see here. It uses TCP, has different limitations and things like that. Or you can have Radius, which is often the one that's used these days. It's a remote authentication dial-in service. Again, this is a little dated, but this is what router devices and network devices would use. It's kind of an open standard, and that's the reason most will use a Radius typical server. Again, it allows you to do password encryption. It has extensive accounting as to what you can do, etc. So, for example, if you have things like an ISP that's allowing remote access and things like that, like when you used to use dial-up, those actually all connected back at some form of a Radius server that provided access to go back through. VPNs are going to be a virtual network that's created over a public network, typically the internet. However, a VPN is going to allow virtual connections routed through the internet to a remote site. So if you're using this in a logical sense, if I'm at home, I can VPN into my corporate network, and that allows me to be as if I'm on that current network. It also allows the VPN concentrator to put security connections in place. We don't want to allow connections straight from the internet. In other words, I shouldn't be able to be at a coffee shop and using the open Wi-Fi there to connect back to my corporate network. That would be bad. Anybody can sniff that traffic and pull that out. So I need to lock it down with a VPN, which is typically encrypted. is software on my machine that creates a secure tunnel back over to my corporate network, and then puts me on a different zone that will also have policies and procedures there as well. And so VPNs can either be formed at a layer 2, which just makes it seem like it's a physical connection, or you can do it as a layer 3 and it puts you on a separate routed network. All right, so to review everything that we covered, networks are going to be typically represented as either physical or logical topologies. A physical topology is going to represent the physical connections and how end devices are connected, whereas a logical topology is going to focus on the standards and the protocols, IP address, that kind of thing that are on the devices themselves. The two most common types of network infrastructures are going to be LANs and WANs. The campus wired LAN design is going to consist of a access, distribution, and core. However, that can be collapsed down from the distribution and core sections. Common security architectures are going to define boundaries of traffic entering and leaving a network. You're also going to have different types of firewalls. So we have packet filtering firewalls, stateful inspection firewalls, application gateway, and then the next gen firewalls that can do pretty much all of that. We have IPSs, or intrusion prevention. Remember, this is going to try to stop it before it ever comes in. And then intrusion detections are used on the network itself to alert and stop unsafe traffic if it recognizes to a particular signature. You're going to have specialized security appliances that are available from Cisco, such as Cisco Advanced Malware Protection, Cisco Web Security Appliance, and their email security appliance. If you want to do a basic low level, you can do ACLs, which are just statements that are going to control whether a device can forward or drop packets. This isn't a firewall. This is actually done on your switches and routers. And there's two different types of ACLs. You have standards and you have extendeds. The standard ones are just going to deal with IPv4 destination IPs, where the extended ones can deal with both TCP and UDP ports for sending and receiving, as well as destination IP addressing and source IP addressing. SNMP is a monitoring protocol that we're going to use to manage network performance and solve network problems, as well as do device configuration inside of there. Netflow is a Cisco proprietary protocol that's used to give statistics on packets that are flowing through the network. This is how I can figure out how much traffic is going to Steam or gaming traffic or web traffic or FTP traffic, etc. That's going to flow through a router or a multi-layer switch. And then if I want to see what's going on a particular network, remember I can't directly connect to a switch. I have to use what's called port mirroring, which is a feature that allows me to duplicate the traffic from one port to another port that allows me to send it out to a network monitor. And this may be something like Wireshark, or it could be sending this out to a IDS, IPS, that kind of thing. A Syslog server is going to compile and provide information from all the different networking devices. It could be web servers, routers, switches, firewalls, etc. It just is a focal point for all of your logs to come in. That way, when you're searching and doing troubleshooting, you can get everything on the same page. You can start filtering and organizing that data. An NTP server is going to make sure that everything is on the same time. That way, when you're troubleshooting, you're not finding inconsistencies across different timestamps and logs. On AAA, it's going to be a framework for configuring user authentication, authorization, and accounting. The ones that are typically out there are TACACs and radiuses, with radiuses being more popular as they are open source now. TACACs is Cisco proprietary. And then for VPNs, they're virtual private networks that connect to endpoints across a public network. And that concludes this section today.